Hey there, welcome back. Today we're going to be talking about minerals and their properties. This is one of the most fundamental parts of learning geology or any earth science is understanding the minerals. Now, prior to watching this video, you want to make sure that you've gone through the previous lecture on the atomic nature of matter that I posted to the class. You want to make sure that you have a good understanding of why elements bond, what the difference between a compound and an element is, and also you want to make sure that you have some kind of general understanding of what a covalent bond is going into this. So that video talks about all of those things. All right, with that said, let's jump right into it. Here we've got some minerals just to kind of whet our appetite. Minerals are beautiful things. We have labradorite plagioclase, which is a type of a very common mineral on Earth, but the labradorite variety is actually really beautiful. It gives you this green and yellow and blue color. Elbaite, which is another mineral that is used in some gems. Of course, gold, right? This is actually a mineral. Gold is a mineral, not just a metal. And it grows in this crystal shape like this, right on another mineral named quartz. Quartz is this stuff right here behind it. And then another really beautiful mineral is this mineral called natrolite. Natrolite forms these nice needles that come out, all radiating out from what they call a nucleation point, a point of where they all start growing out. I always use the analogy of a chia pet. Those of you that have any memory of a chia pet will understand what I'm talking about. The long chains of letters and numbers here are basically the number of atoms in the molecule. So the basic unit of all these is an individual molecule. And some of these are really simple. Look at gold. Gold is one atom. It's not even a molecule. It's actually an element. So it's one atom all linked together. It's gold. But quartz is pretty simple. It's one atom of silicon and two atoms of oxygen right over here. And that makes this white rock behind it. But by comparison, look at this mineral over here. Okay, it's got sodium, lithium, aluminum, more aluminum, silicon, oxygen, boron, more oxygen, and then the OH4 is actually a series of waters, because remember water is H2O. So this is a relatively complicated chemical formula. Fortunately, it's a very rare element, or I'm sorry, a very rare mineral on the Earth. But nonetheless, you get an idea of how complex some of the minerals can be and how simple other ones can be. Natrolite also, again, sodium, aluminum, silicon, oxygen, and then with two waters actually in there. Labradorite is actually relatively simple by comparison with these two here. All right. So let's talk about some of the properties of minerals. And one of the most obvious properties that minerals have is their luster, which is to say how they reflect light. And it's their luster that we really care about if we're looking at something as being possibly a gem. So just for your benefit, as I've gone through, I've tried to give good examples. This is a fluorite crystal growing here. These are galena crystals down here. The chemical formulas are usually put right here in parentheses just for your own understanding. So as we go through, I'll point these things out. So luster is the appearance of a mineral in reflected light. So there are two basic categories. There's metallic and non-metallic. And you can tell right away, this looks like a hunk of metal down here, and this one most certainly does not. It looks almost like a glass bead, if anything. So this one would clearly be metallic and non-metallic. The fluorite would be non-metallic. Other terms are used to further describe luster, such as vitreous. Vitreous is just a fancy way of saying glassy. Silky, talc can be silky, or earthy. Talc can also be earthy. Talc is another mineral that we see used in baby powder, for example. All right, so the way that it reflects light is an important property of minerals. It helps us to identify them on the spot. Another thing that minerals have is color. But the problem with color is that it's generally an unreliable diagnostic property to use for mineral identification. Why? Well, look at this. Here are varieties of quartz. Remember that white mineral I had back here? I'm just going to go ahead and move back to the beginning. This back here, well, here it is again. Here's a black variety called a smoky quartz. Here's a purple variety called an amethyst, white quartz, and then another one that is stained orange or almost a reddish orange, which is a variety of rose quartz. But it's all quartz. So could we say that quartz is always white or always black or always purple? Of course not. We can't make that determination. Quartz, it turns out, has many different colors to it. Okay, so it's often highly variable for a given mineral because of slight changes in mineral chemistry. So a little bit of impurities that get in here that cause these differential colors. Exotic colorations of some minerals produce gemstones. For example, amethyst. Amethyst is quartz. It's just common quartz with a simple impurity that makes it this purplish color. Okay, azurite is another beautiful one. Aquamarine, and you can see that we have the whole rainbow right here, right? Red, orange, well, the orange one is missing, but red, orange, yellow, blue, indigo, violet, right? The colors of the rainbow are all seem to be represented here. And yes, there are in fact orange minerals. Just because there's one there does not mean that it doesn't exist. So keep that in mind. So one thing that is really cool about minerals, I mean, you could take a mineral and you could take a, for example, I'm holding a mineral in my hand. This is the mineral galena, as you might remember from the very first slide I showed. But it's a metallic mineral, and if it had any impurities in it, or if I had another metallic mineral, I might not be able to identify it very easily. It does turn out that minerals have this really cool property that you can crush them up into powdered form, which is very easy to do using something called a streak plate. And unfortunately, I don't have a streak plate here, but there is one pictured here. So this would be a streak plate right here. And you can see that this is in fact galena that's being dragged across the surface of the streak plate here. And notice that the streak color is different than the color of the rock itself. That difference is diagnostic of the mineral. So it turns out that this is common for minerals like hematite or galena. Actually, this is the mineral hematite. I'm sorry, I kept saying galena earlier. I was holding galena. This is hematite right here. And hematite produces this reddish brown streak, which is very diagnostic of hematite. Well, in your hand, if you were holding that color of hematite, called specular hematite, and galena in the same hand, you might not be able to tell the difference between the two. Okay? So what does that mean? It means it's helpful in distinguishing different forms of the same mineral. So the powdered forms sometimes give its true color that the surface or that the larger mineral surfaces will not give you. That's really neat trick that we can use to figure out what kind of minerals we're dealing with. Another thing is their hardness. Not all minerals are the same hardness, right? And what is hardness? Resistance of a mineral to abrasion or scratching. So you can take a mineral and you can scratch another mineral with it, and the one that scratches the other one is the harder of the two, right? And so we've got a system that all minerals are kind of thrown into. Let's just say all minerals are compared to a standard scale called the Mohs scale of hardness, Mohs hardness scale. And you guys have probably heard this at some point, but diamond is going to get a 10. It is the hardest mineral. It is the hardest naturally occurring substance on the planet that we know of. So it gets a 10. And one of the softest is this mineral called talc. I was just talking about a little earlier. This is what we grind up and put into baby powder. We put it into baby powder, why? Because it's so soft, right? That makes sense. And then it goes in steps, right? Another common mineral is gypsum, which we use for making drywall. Calcite, this is what reefs are typically made out of. Fluorite is the mineral that we grind up and we put it into toothpaste. Apatite, again, related to your teeth, that's the enamel on your teeth that make your teeth hard. Feldspar is a really common mineral that exists. As a matter of fact, it makes up 50% of the Earth's crust. Different feldspars, and they get a standard strength of about 6 or a hardness of 6. Quartz is heavier than that at 7. Topaz, which is a common gemstone, semi-precious gemstone, gets an 8. Corundum, 9. And then finally diamond, of course, which is rare, but also very beautiful and extremely hard. Okay, another really cool feature of many minerals is something called cleavage. And cleavage is basically the tendency of minerals to part or to separate from itself, right? So you might have a mineral and you can put a little pressure on it and it'll start to shear off and form these little plates here. In this case, this would be a blocky mineral, probably something like table salt, which is a mineral called halite. These big blocks will separate off into smaller blocks. And this is really a common feature in minerals. So they're described by resulting geometric shapes, such as number of planes or angles between adjacent planes. So for example, here we have calcite, which is a common mineral. Look at this. If I was to break it, look how flat that surface turns out to be right on top. But also right here on the side, this side here. So we would say this has cleavage on 3 sides. Here, here, here. Fluorite is even cooler. It has cleavage on this side, on the other side, and the other side. So 4 on the top, but look, it does it again down here on the bottom. 1, 2, and then 2 on the other side. So this is be 4 planes of cleavage right here in just a single mineral. And look, you can even see it's already starting to part right here. You see this orangish zone with the red zone right next to it, and there's a flat plane right here between it, again right there. So you can see there's actually additional cleavage planes even inside the crystal. They're not always up here on the surface. That makes cleavage really neat. And this is a diagnostic of fluorite. Fluorite has these famous 8 planes of what we call perfect cleavage. You get other ones that don't break so perfectly, and you get kind of a rougher form of surface when you break them. And eventually we'll come to that. So here's some typical cleavage directions that we see in minerals, in beautiful mineral samples. We get the most famous example, which of course is the muscovite cleavage that occurs in one direction. Basically it forms sheets, right? Almost like pieces of paper. And in fact, muscovite, which is the most common example used here, is called a phyllosilicate, which means a sheet, silicate, because it looks like a sheet of paper. All right. Here's the one for feldspar. Look at this, 90 degrees, right? Here's one on this surface, one here. That gives you that nice 90-degree angle. But that is only on 2 sides. This other side over here is a fracture. So you only get cleavage here on side 1 and side 2, but not on side 3. So that's a different kind of cleavage than what we see here, which is cleavage in 2 directions, not at 90-degree angles. Here we see it at 90, but here it's at 120. And you can see it here in this rock. All right, perfect cleavage in 3 directions at 90 degrees. Typical is halite or table salt. And look at this. We have it on this side, and right here up on top. They're at 90 degrees, right? These steps are all at 90. And then here's the mineral halite. Again, 3 perfect cleavage planes, but notice that it's not at 90 degrees, 75 degrees here, okay? You can figure out the geometry of what it must be on the other side. I'm not going to give that away. You might have some fun figuring that out. Put that in the discussion board. That'd be neat. Up here on top, we have a nice flat plane. So 1, 2, 3 planes, but not at 90 degrees. And of course, we just mentioned fluorite having 8 sides, but 4 directions, right? 1, 2, 3, 4, and then it reverses to the opposite side of the top here. And we wind up with 4 perfect cleavage planes. Another really cool property of minerals is not only do they not always have cleavage, right? If you just kind of looked at the examples I just gave, you would assume that all minerals would have cleavage. And we'll talk about why you might think this as we go forward into the lecture. We're going to talk about what minerals are on an atomic scale going forward. But some of them have some other really cool features. For example, here's quartz. Turns out quartz doesn't really have cleavage. But when it breaks, it forms what we call conchoidal fracture, which means these circular breaks. And you've seen it probably in window panes, right? A broken window will have this nice curved, as opposed to a nice, instead of having cleavage, it'll have this nice curved fracture. And we call that conchoidal fracturing. And that occurs when there's an absence of cleavage when a mineral is broken. Another thing that is important is specific gravity, which is the ratio of the weight of a mineral to the weight of an equal volume of water. It's a comparison, right? So usually water gets a value of 1. So average value for quartz, for example, is 2.7, which means that water is 2.7 times heavier than water. That's all it means. Don't let it freak you out too much. Some things have really high specific gravities. Things like iron oxide have ratios that are over five times heavier than water. And then there's other things that are, certain rocks like pumice, which actually have specific densities of less than 1. They float on water in some cases. There are other really neat physical properties of minerals, right? Magnetism, right? Not all minerals are boring and don't do much. Some of them are magnetic. Here's a big piece of magnetite, which is Fe3O4. Anybody that's interested in the chemistry will realize that there's one ferrous and 2 ferric irons in here, and then 4 oxygens. But if you're not interested in that sort of thing, don't worry about it. It's just for the people that are really into chemistry that might be interested in this. But anyways, here you have this huge lump of magnetite, and it's completely magnetic because of the differences in the iron electron clouds. Reaction to hydrochloric acid. If I take some hydrochloric acid and put it on here, nothing is going to happen. It's kind of a boring thing when it comes to hydrochloric acid. But if I put it on a mineral like calcite, which I've already mentioned, it actually creates a huge reaction. You'll see bubbles come up all over the place. Malleability is basically the ability to take a hammer and just bang it into very, very thin sheets. It turns out gold, you can bang them into sheets so thin that light will actually go right through. Amazingly malleable. Double refraction, which is the ability for light to go through it, almost kind of like a piece of glass, except in the case of double refraction, you don't just see the light come through and you see the image, you see it twice. So it doubles it up in the image as it comes through the crystal. Again, calcite does this. Some minerals have an interesting taste to it. Some are earthy, some are kind of bitter, whatever. You wouldn't want to go around putting some minerals in your mouth. Some of them can be toxic. Some have a distinctive smell, like sulfur. Sulfur is usually an S8 molecule in nature. And some of them are elastic. You can take a crystal and you can bend it and it will return back to its original shape. Really neat stuff, right? So you have to keep in mind that crystals and minerals are like people. I mean, they have their own personalities in many ways. And sometimes you find a unique and rare mineral specimen. It might be one of only a few known copies of that in the world. So mineral collecting is a huge hobby for a lot of people, and there's a huge online following for mineral collecting. So if you have anything interesting or want to show anything off, you can go on, you can get a starter kit. This is actually a starter kit I got from Amazon.com. I'll show it off a little bit. Here's another metallic mineral, chalcopyrite. Really beautiful mineral, almost goldish looking, and you can get a whole mineral set started for probably 30 bucks if you wanted. All right, so the real question then is, okay, so we have this Earth. It's made up of atoms and molecules. What is the main composition? What is the main mineral chemistry that dominates everything? Well, that depends on what the Earth is actually made out of, right? Because you can only make minerals out of what's there. And so here's the composition of Earth as we know it. Here's oxygen. It turns out most of the Earth is made out of, or at least the crust is made out of oxygen, strangely enough. A lot of people don't think about that. Silicon. Silicon is 27.7%. Aluminum is another huge part, right? If anybody asked you what the Earth was made out of, most people would say it's probably made out of silicon and iron. And that would be the first two that most people come up with. But no, it turns out it's oxygen, silicon, aluminum, and then later on there's some other elements: iron, potassium. Potassium's a big one. Magnesium's an important one. Sodium, calcium, and then look at that. 1.5% is all the other elements. Gold. That's where your gold and your platinum and your copper and your silver and your mercury and you name it. All that stuff that goes into the Earth is in that little 1.5%. So the Earth is really just a giant ball of silicon and oxygen with some aluminum and iron thrown in. Think of it that way, okay? And so that means that there really aren't that many major rock-forming minerals. Even though there's been 4,000 minerals identified on Earth, you really only need to know about 15 to really get an idea of what the Earth is doing and know it well. So the common minerals that make up most of the Earth's crust is called rock-forming minerals. Only a few dozen members. It's really actually easy to remember. It's easy to actually get a collection of all of them. They're everywhere, and you can anything you can't get yourself, you can order online and have shipped to you at very low cost. You can get beautiful quartz crystals sent for a couple of dollars, and they're beautiful. These are composed mainly of the 8 elements that make up more than 98% of the continental crust. Okay, so as we've already covered. So what kind of minerals do we see coming from these 8 major elements? Well, the first group that we see that comes along is the silicates, right? That makes sense, right? I said that silicon and oxygen are the 2 most common ones. So let's talk about silicates, which is silicon and oxygen. So it by far is the most important mineral group, and it comprises most of the rock-forming minerals on Earth. So if you don't know your silicates, at least know a little bit about them and their distribution, then geology becomes a lot harder. But this is really kind of a neat group, and it's kind of easy to follow if you pay close attention. They're very abundant as a result of large amounts of silicon and oxygen in Earth's crust. We just mentioned that. Basic building block is the silicon-oxygen tetrahedron molecule. And what is that? So here's the tetrahedron molecule. Let's describe it. 4 oxygen ions surrounding a much smaller silicon ion. So this is what it looks like. And you put basically a little silicon, this blue thing. Here it's expanded out so that you can see it a little bit better. But here's the silicon, and there's 4 oxygens. And notice that it's basically forming a pyramid. And the pyramid shape in geometry is referred to as a tetrahedron. That's all it is. When we pull it all together the way that it looks in nature, it actually looks much more like this, right? The silicon is buried in the middle of these 4 very large oxygens. So the oxygens take up most of the space in the tetrahedron. And this is the building block for almost all of our minerals. And so we're going to use this tetrahedron. You're going to see this coming up as being one of the most important things that you come out of this lecture, or hopefully that you take out of this lecture. So remember those tetrahedrons. Let's not forget. This is what this is. You're going to see this basically means an SiO4. SiO4, silicon with 4 oxygens. So here's the different mineral structures that we're going to see. And basically, they're single tetrahedra that are linked together to form various structures. And the main ones are the isolated tetrahedra, which is this one, a mineral that basically has the silicon. There's stuff around it, but we'll come to that later. The tetrahedral pairs, right? You can get tetrahedrons that connect and form these pairs. You get a ring structure where tetrahedrons will form a 6-sided star. Single and double chain structures. So here's a single chain where they alternate back and forth, back and forth, back and forth. And then the double chain is just simply this chain linked to another chain to form this here, right? And this looks basically like the ring structures all linked together. So you can see that there's kind of some simple patterns that start to repeat. And then you can take these and you can actually double them and add and attach them to another double chain structures in infinite number of directions. And look at this, you wind up with a whole sheet, or what we call a sheet or layered structure. And then of course, what I can't show because it's just simply too complex are the 3-dimensional structures. We will show one a little bit later regarding quartz, which is formed this way, SiO2. But this is the typical forms that we see of silicate minerals. And so we can rapidly recognize how important these little tetrahedra are. Remember, the tetrahedra is a single silicon with 4 oxygens surrounding it. So let's look at how these things form minerals. So here is a mineral called a smectite, which is a clay. It exists all over the world. It's a common one. And here we can see we got these the silicate layer sitting up here on top. And down here on the bottom we see another one. And then sandwiched in the middle is the aluminum hydroxide. So here we see aluminum and water smashed in between. And these things form these what we call silicate sandwiches. And so this is what clay looks like. believe it or not, clay is a crystal, a series of crystals. And it's got silicon, aluminum hydroxide, silicon, and look, they're connected all together with potassium ions. Silicon, again, repeats, silicon again. So this whole thing, this sandwich here on top, sandwiched down here on the bottom, connected by the potassium, that is a clay crystal. I think that's absolutely fantastic, right? So to join these things, most silicate minerals have a negative charge, right? So we need to balance those charges. That's basically what's happening here by combining it with these metal ions in here and in the aluminum hydroxide layer as well. These positive ions bond with unshared oxygen ions in the tetrahedron, and metal ions are required to balance the charge, right? Because this is a negative, see that's a -4. You need some positives to balance it all out. That's what these guys do very well, and that's what some of the stuff in here also happens. Neat, right? It's a little complicated at first, but it's really not. It's really not that sophisticated. Just remember, they're just little pyramids, silicon and oxygen, trying to find a way to balance themselves out. All right, so there's some other really cool structures. Remember I said there was a 3D framework structure for quartz. Now look at quartz here. This is SiO2. Notice it doesn't have any nice sheets to it at all, right? But over here, talc, which is, remember that baby powder mineral I was talking about earlier in the lecture? Look at this, nice sheet structures in here. These nice sheets slide past one another. This is the reason why talcum powder is so soft. But quartz, which doesn't have any sheets in it and doesn't want to separate and doesn't want to form any cleavage or anything like this, is so gritty and hard and so resilient. So you can see how these things are all combined, right? End to end, tip to tip. And in this one here, they've actually put the oxygens at the corners of the tetrahedron, but here they've left it off. But you get the idea, it's the same stuff. So what kind of bonds control the situation? Well, covalent silicon-oxygen bonds are typically stronger than the ionic bonds of the silicate structure. So what does that mean? That means that, generally speaking, far and away the prevailing type of bonding you find in the silicates are covalent bonds, right? So examples are, or it controls the cleavage and hardness of minerals. We just talked about that with talc and with quartz. And examples, quartz has a three-dimensional framework, is very hard and lacks cleavage. Talc has a sheet structure framework bonded with magnesium ions and is a very soft mineral. So yeah, talc is, even though it's this nice white mineral, it actually has magnesium in it, which usually in nature occurs as a darker mineral. So you'll realize pretty rapidly that color is not diagnostic of the chemistry. And so with that said, that kind of leads us into this two groups of minerals that we see over and over and over again in nature. There are the dark minerals and there are light colored minerals. And the main reason why we see the difference between them is the composition or the chemistry of the minerals. So dark silicate minerals usually are black, gray, or green in color. So an example would be olivine or augite. Notice that olivine is green and augite is this black color, and hornblende is black. Biotite is black. This is another one. Also tend to be dense, which is to say heavy for their size. So the dark color and higher density are due to the presence of iron and magnesium inside the crystal. Such minerals are considered to be ferromagnesium. That means iron, magnesium crystals or minerals. But we don't always say ferromagnesium. That's a hard way to say it. The way that we actually call it is mafic. We actually take the Ma off the magnesium and the F, and we just say mafic is the shorthand way of saying it. So mafic minerals are these black ones. And so from here on out, just know that ferromagnesium, which means iron and magnesium bearing, is shorthanded to mafic. You'll hear me say that a lot. Light silicate minerals are less dense than mafic minerals. Why? Because they lack iron and magnesium, which that makes them lighter in color as well. Group is dominated by quartz and feldspar, and instead of saying mafic for this group, we call them felsic. Obviously, because sic is silica and fel is feldspar. Felsic is the shorthand way word for this group. So felsic versus mafic, you'll hear both of them. So light colored rocks tend to be lighter in weight or in density, and we call them felsic. The heavier ones are ferromagnesian. They contain iron and magnesium. We would say that those are mafic. So let's talk about the main felsic minerals, quartz and feldspar, as we go forward. So the group that is most important are the feldspars. Why? Because the feldspars are the most common silicate group and make up more than 50% of Earth's crust. There are two main types, right? And I've got them right here. The potassium feldspar, which is also called orthoclase, so potassium feldspar, and plagioclase feldspar, which is this white to grayish mineral over here. Quartz is the second most abundant mineral in the continental crust. And notice it's not in the oceanic crust, only the continental crust. You will find the feldspars, however, especially plagioclase, in the oceanic crust. You'll rarely find this one here, but this is a big part of the oceanic crust. Anyway, quartz is the second most abundant mineral in the continental crust and the only common mineral made completely of silicon and oxygen. So silicon and oxygen is all you're going to find in quartz. Once you get into plagioclase and potassium feldspar, obviously it's called potassium feldspar because there's potassium in it. But there are other elements that are mixing in here to create those minerals. Move the cursor over here. So we can't actually start our discussion of minerals unless we start with the most basic silicate, and that's quartz. Right? The quartz is SiO2, just common SiO2. It's made of oxygen and silicon. It's hard and resistant to weathering. It's got conchoidal fracture, right? It doesn't have any cleavage, right? This is actually the crystal faces on here. This is not cleavage here. If I was to break this, it would form conchoidal fractures, that rounded fracture pattern that I showed you earlier in the lecture. It often forms hexagonal, which is a six-sided crystals. And so you'll see 1, 2, 3, and then on the other side are 3 more. So that means as you go around, you'll see 6 sides to that crystal. And it's typically colored by impurities that creates numerous varieties, including gemstones, right? Amethyst, citrine is another common one. Jasper, onyx, tiger's eye, carnelian. These are all varieties of a simple formula called quartz, SiO2. They're all varieties of exactly the same mineral. Okay, the feldspars are the most common mineral group, and they form under a wide range of temperatures and pressures, which means you find them all over the place. They form in all kinds of different rocks. They don't only form in one group or another. You'll find quartzes will be present in some things and not other things, but in terms of feldspars, you find them everywhere. They exhibit 2 directions of perfect cleavage at 90 degrees, right? So they're kind of sitting there just like so. And if you don't remember what 90-degree cleavage looks like, go back in the video and find where we talk about that. The 2 most common members are orthoclase, which is potassium feldspar. That's this pink stuff up over here. And it's got this formula, potassium, aluminum, silicon, and oxygen. But this is the main thing, right? The potassium here. And it turns out the most common variety is this pink kind of orthoclase or potassium feldspar, same thing. But there is a rarer form of it, this green type of potassium feldspar, which is called amazonite. Typically, we just refer to it as K-spar because it's potassium feldspar, and this is the symbol for potassium is the K. So we call it K-spar. And then plagioclase is this group down here, and there's a wide range, right? So there's sodium plagioclase, which has got sodium with the same, you'll notice aluminum, silicon, and oxygen, aluminum, silicon, and oxygen. That's why they're the feldspars here. So the sodium plagioclase gets its own name, and it's called albite. So this is the sodium plagioclase albite right here. And the calcium plagioclase variety, which is chemically slightly different, is called anorthite. Why is it chemically slightly different? Look, the number of silicones here is 3, here it's 2, but here the aluminum is 2, and here it's 1. So it's just a redistribution of what we call the electrons across the crystal lattice that allows for extra aluminum to be in the mineral. So there's more aluminum here than there is over here. All right. So we can't really move forward until we bring up a special case, something called a solid solution and alloys. Solid solutions are hybrid minerals. And feldspars do this all the time. They create these hybrid minerals. So we were talking about perfect forms, right? Let's go back to this. This is perfect potassium feldspar. This is perfect sodium feldspar. And this is perfect calcium feldspar, also known as K-spar, albite, and anorthite. Well, when we come over here to the K-spar, which is also orthoclase, remember it's all the same stuff. In feldspars, the K in the KAl-Si308 or orthoclase crystal lattice can be replaced by sodium, the ion in albite, creating a hybrid chemistry, right? So occasionally you might put in a sodium here instead of a potassium. And so this blends the two, right? It's not pure orthoclase and it's not pure albite, it's a mix. This replacement can occur because sodium is close to potassium in size and they have the same ionic charge. So it's okay. The crystal is totally fine saying, yeah, I'll go ahead and take an occasional sodium and put it in here. No problem. And the two pure minerals in a solid solution are called M members. So you could take some albite, you can take some orthoclase, and you can mix them along some percentage. So 50-50, it lands about right there, right? Because that would be 10, 20, 30, I'm sorry, 10, 20, 30, 40, 50% would be about right here. And this would form a mineral called sanidine, which is just basically a hybrid mineral between orthoclase and albite. And the reason why we got to bring this up is because many minerals exhibit solid solutions. So orthoclase makes a solid solution with albite. In other words, they mix and form a hybrid somewhere between there. And the same thing will happen between albite and anorthite, right? We've already brought up labradorite. Well, labradorite is right here, okay? It's a form of plagioclase. It's right in between those two. Now notice these two won't mix. There's nothing in here. These two will not mix, the anorthite and the orthoclase, but through albite they will. Many minerals exhibit solid solutions. Okay. Kind of right on the tail end of what a solid solution is when we talk about metals. So in crystals with metallic bonds, these solid solutions are called alloys. So it turns out gold, silver, copper are three metals, and we can put them all into a mix together, and they'll form crystals, actually. And so it turns out that gold, silver, and copper will form these alloys, and you can put together percentages, right? So you could mix gold and copper, and it will actually form a metal that's about this color, what we call copper red. If you have white gold jewelry, it's probably over here somewhere between silver and gold, right? Mixed in here. You want to know what color pure gold is? Well, it's actually a reddish yellow color. It's not actually this yellow that people usually associate it with. So anyways, you get the idea that on this diagram, we have three metals and we can mix them together and we can see what we're going to get. If they were in fact mixed 50-50-50, it would be right here in the middle of the diagram and be yellowish in color. Why is this important? Well, how about for the production of steel? Well, steel is an alloy of carbon and iron. So here we have steel. It means every once in a while in a crystal lattice of iron, they've replaced some of the iron with carbon, and that makes steel. That makes it a lot harder, a lot stronger, and a lot more useful in industry. Pure iron is relatively soft and heavy. Steel is light and very strong by comparison with iron, and to be preferred in almost all building construction. Stainless steel, on the other hand, is an alloy of steel. Remember, steel is already an alloy, but steel, corundum, and nickel, which makes it an alloy of an alloy, which is kind of cool. So you got to take some steel, which is iron carbon, mix in some chromium and some nickel, and you wind up getting stainless steel in the right proportions. the diagrams and the chemistry are a little complicated, which is why I don't have it on here. But I just want you to get the idea that you don't have to have everything super pure. You can put in impurities, and those impurities can actually strengthen it or change the characteristics of it. And this is important because the Earth is doing this all the time. The Earth is this giant chemistry set, cranking out new minerals all the time that fit its need at that time. Volcanoes especially are notorious for as giant chemistry sets. All right. So anyways, you can't really understand solid solutions and alloys and be, say, a metallurgist or some type of metal engineer. You have to know these things. All right. So let's go through the next one, right? So we've covered quartz, we've covered feldspar, and now we've covered the solid solutions. Well, the next mineral that I think we should really get to know something about is this mineral called muscovite. It's kind of a funny sounding name, but we'll come to by the end of this, you'll know why. So it's a common member of what we call the mica family. Micas are these minerals that form these sheets. And look, you can actually see right through this mineral right here. It's actually, light transmits through it. It's got excellent cleavage in one direction. We would actually say perfect cleavage, right? That perfect cleavage that breaks it off into sheets. Here we can see it over here breaking off into sheets and forming this nice star form on the front of this rock. The thin sheets are clear. You can see right through them. And they were used as glass during the Middle Ages, especially in Moscow. And here you can see where it gets its name from. Somebody that is born and raised in Moscow is referred to as a muscovite. Well, that's the name of the mineral, right? It's basically a person from Moscow. It's called a muscovite. Produces the glimmering brilliance often seen in beach sand. We don't see this here in Hawaii, but if you're in California or if you are on the east coast of the United States or on a lot of coastlines in China and in India, you would see this frequently. And here's the complicated chemical formula. The only thing I want you to take out of it is not only does it have aluminum and silicone on it, but it has water in it. And when we get into talking about volcanoes, you'll understand exactly how important minerals with water are. So muscovite's got water. That's important. Another really cool felsic mineral are the clay minerals. We've already talked about, I showed you kind of a diagram of the sandwiches of silicate with the aluminum hydroxide in the middle, put together by the potassium ions. If you don't remember that, you can go ahead and review the video at this time. But anyways, what does this actually look like then in real life? Clay, right? We don't really think of clay as being anything other than just a smushy thing, right? Well, it turns out they're crystals, just like anything else. And so it turns out clay is just a general term used to describe a variety of complex minerals that have sheet structure. So clay makes up a large percentage of soil, and one of the most important ones is kaolinite, which is a common clay mineral used in the manufacture of fine china. As a matter of fact, I believe the name kaolinite is from the town of Kaolin, which is where they invented Chinese porcelain. All right, so, and here we see very, very, very detailed images of clays. This is, I believe, a series of smectite clays right here. And you can see that these crystals, even though they're all folded up, they're really, really soft. But those are crystals nonetheless. Here you can actually see it. It's just a nice little sheet of clay right there. Up here, we see another variety of clay. This is, I believe, actually kaolinite. And kaolinite forms these books, right? You can see these books are almost like little tiny caterpillars stuck in here, all piled up and around. Here's a big piece of quartz right here, but this is little bits of clay. And so on a microscopic level, and when we're talking microscopic, we mean like you got to use an electron microscope to see it. Really, really small stuff. You finally start to actually see the crystal structure for the first time, right? So it's so small that you can't see it or even feel it, but it's definitely there. That's what clay looks like on a microscopic level. All right, so let's switch gears. Let's go from the felsics, as cool as those are, and let's talk about the mafic minerals. Now the mafic minerals I put second because they have a strong tendency to create solid solutions. And so it takes a little while sometimes to kind of wrap your head around this. But the first group I want to talk about are the olivines. Olivines are extremely common worldwide. What is an olivine mineral? Well, it's a high temperature silicate solid solution mineral. They tend to be black to green in color. Red and yellow varieties also exist. I've seen both. I've seen them almost a goldish yellow color. They're fantastically beautiful when that happens. They usually have a glassy luster. So here's a typical olivine crystal. Look how glassy that looks like. It looks like a glass bead. And some people think it's due to a nickel impurity that turns it that green glassy color. And it has conchoidal fracture, so it doesn't have any cleavage on it. Remember the muscovite and the plagioclases had that. This doesn't. This is more like quartz. And it's very hard. It has a hardness of 6.5 to 7. Quartz has a hardness of 7. So in a lot of ways, it has a lot of features, physical features similar to quartz. Forms small, rounded crystals. The gem version is called a peridot or a crystallite. So a lot of you have had some experience with a peridot at some point. And it turns out there are two end member varieties that form a solid solution. One is called forsterite, which is a magnesium silicate, and the other one is phaolite, which is an iron silicate. So what do these two look like separately? So let's look at the end members. Well, here's forsterite. Look, it's this beautiful, clean, clear crystal, but it's very rare. It's rare to find the pure end member. And this was actually found in a special mine in Germany. Over here is phaolite. Phaolite is this red, it's red because it has iron in it, iron silicate mineral, and it is also very rare. What is not rare is to find the green olivine crystal that we are so familiar with worldwide. It's called olivine because it's olive colored. And the general formula, therefore, is magnesium iron silicate. It's this right here. You don't have to write down all these things, but I just want you to understand the color relationship to the chemistry, that these are very closely tied to one another. Another really cool group of minerals are the pyroxenes. They're mafic, just like all the others. And they're important components of dark-colored igneous rocks. There are two principal types. There's orthopyroxene, which is sometimes shorthanded to OPX, and clinopyroxene, CPX. Don't worry, we're not going to get into the detail. That's more of a, just to let you know it can be subdivided. Of the two groups, there's two really common or very important minerals. So we'll talk about the OPX variety here first. So enstatite is an important OPX mineral with a simple formula of magnesium, silicon, and oxygen 3, right? MgSiO3. It's green to black in color and has been detected outside of our solar system. This is enstatite up here. That's what's really interesting to me, is that it's actually been detected in some solar systems that they believe are developing way far away from our own. So it's an important mineral cosmically to have a good understanding of. The other mineral that is really neat in the system is augite. Augite is the most common mineral in the CPX group, which is a clinopyroxene. So the chemical formula is this really nasty thing right here. Don't worry about this too much, but here's the mineral, augite right here. And it tends to be black in color, two distinctive cleavages at nearly 90 degrees. You can't really see those cleavages here because the mineral is so pristine. But if I was to take a hammer and say shatter it right here, you'd see it. And what's really important about this is it's the dominant mineral in basalts. And this is the reason why basalt tends to be black in color. It's because of this mineral augite. All right, so our crusade through the minerals continues. Let's continue with the amphibole group. The amphibole group, the main mineral in here is hornblende. And hornblende is all over the place. It's present in Hawaii, it's present all over the mainland, it's present worldwide. This is a major mineral. The cool thing about this one is, other than the fact that it has perfect cleavage, is look at the angle of that cleavage. Here you can see it in this cross-section of a crystal that's been cut by a saw. Look at that, 60 degrees right here and 120 degrees around this way. So this is what they call 6120 cleavage right here. Really cool mineral. It's got calcium, it's got all the cool stuff, magnesium, iron, aluminum, silica. But look at that, OH2, that's water. It's another way of saying water in chemical formula, in chemical form. Cool stuff. So there's a couple other really important ones I want to bring up also, which is biotite, which is the iron-rich end member of the mica family. Remember, we already met the other end member. That's muscovite. So remember, and it's an end member, meaning a chemically pure version that can blend with another one to make a hybrid. So biotite is pretty common. Excellent cleavage in one direction, just like muscovite. And it contains water. Look at this right here. It contains water. Very important volcanic mineral. The garnets, here's a garnet called, garnet variety called grossular. It's composed of individual tetrahedra linked by metallic ions, similar to olivine. So this is actually very similar to olivine in a lot of ways. Glassy lustered and conchoidal fracture, just like olivine. Solid solutions are common. As a matter of fact, they're basically the rule. You'd hardly ever find perfect end member versions of garnet forming. And the chemical formula is this version here for grossular. Now, of course, you can replace calcium with sodium and aluminum with silicon and so on and so forth. And you get other solid solutions. But anyways, really cool family of minerals. But that's just to get through the silicates. Now, the silicates are by far the most important mineral group. So the rest of them are, there's a kind of a short list that are really important, and we're just going to briefly hit those really fast and bring up another mineral property that's really important before we finish this little conversation about minerals. So the important non-silicate minerals are basically divided into groups based on negatively charged ion or complex ions that the members have in common, like sulfates, sulfides, oxides. So that's what we mean by ions. So you can actually have ions that are not just only atoms, but also molecular ions as well. And they make up approximately 8% of the Earth's crust. So these are important. The other 92% are the silicates, but these 8% are important, especially the carbonates. These guys are really big. We're going to talk about them. So the list here are the phosphates, the halides, the carbonates, the native elements like gold, sulfate, sulfides like pyrite. That's another way of saying fool's gold, oxides. And so here's the mineral halite, which is a halide. And of course, apatite, which is up here, is also an important phosphate mineral. So these carbonate minerals are really important, especially when we get into dealing with sedimentary rocks and talking about reefs and things like this. You need to know what a carbonate mineral is. So they're the primary constituents in limestone and dolostone. Calcite, which is calcium carbonate, CaCO3. The CO3 is called the carbonate anion, so calcium carbonate. And dolomite, which is the calcium magnesium version of this carbonate right here, are the two most important carbonate minerals. So here they are. Here's calcite. Here's dolomite. They look pretty similar, but the composition is pretty different. Calcite is the main mineral used by organisms in the formation of coral reefs. Calcite, now this is important, calcite can change to a dolomite over time through a special chemical process called diagenesis. So one of the things that does happen in Earth's history is that minerals convert one to another. And sometimes this makes it a little difficult to put together geologic problems because the minerals are always changing. Especially in diagenesis. But just know that minerals can, under certain circumstances, flip into other kinds of minerals. And kind of leading into that is this idea of a polymorph. All right, so a polymorph is simply, polymorphs are minerals that share the same chemistry but have different crystal forms. We're very familiar with some of these polymorphs. Let's hit these here in a moment. The formation of crystals is highly dependent. Oh, this should say dependent, and I will correct it in the PowerPoint. Highly dependent upon heat, pressure, and the chemical environment. And important examples are graphite and diamond. So these have the same chemical composition. Graphite is carbon, diamond is carbon. That's what this C stands here. They're both made out of carbon. The only difference between them is the the crystal structure. The chemistry is exactly the same, but the crystals are different, right? And that's all a polymorph is, right? Let's reiterate this. Minerals that share the same chemistry but have different crystal forms. Calcite does the same thing. Remember calcium carbonate? Well, calcite forms also aragonite. So here's calcite, that stuff that forms reefs, but here's aragonite, this needle-like mineral that pulls off here. And some of them don't just form one or the other, some form three. Here's kyanite, sillimanite, and andalusite. And they all have exactly the same chemical formula, Al2SiO5. But they're completely different minerals because they form at different pressure and temperature situations. So I know that what we're giving you is really dense material. We've covered polymorphs, we've covered solid solutions, carbonate minerals, many of the silicates, both the felsics and the mafic silicates, as well as many of the physical properties, including luster, cleavage, conchoidal fracture, and color, streak, specific density, or specific gravity, I should say. That's a lot of stuff to take in. But take your time, watch the video again if you have to, and then also make sure that you have the book read before you attempt the homework set. So if you have any questions, feel free to give me an email.